Hello, can you guys hear me? Okay, good evening. Yeah.
Question, do you think you can go over how to do the last problem for the homework for homework three?
Homework three.
Yeah, the last problem.
The last
Yeah,
problem?
very, very last problem. I was kind of off trouble.
Yeah.
You can go over it?
Not today. We don't have time today.
Okay.
But it's not going to be tested on the quiz.
Okay.
Well, I'll probably we'll have some stuff similar to that.
Okay.
But yeah, it's kind of repeated so many times. Hopefully, you guys will get good at it. Yeah. Okay, so just welcome back. And you know that we're gonna have a quiz today towards the end of the class. Um, I did put it on. You cannot hear? I mean, hold on. Maybe close. Yeah. Is this right? Is it better? Okay. A couple announcements. We're gonna have a quiz today at 6, probably more like a 5:55. And next week, you guys gonna watch the recorded lecture. Uh, the two lectures, one is gonna cover the last part of chapter 8, and then also the next lecture is gonna cover the first part of chapter 9. Now there'll be a little bit of contents from chapter 8 that's not covered, so I'm gonna do it again on February 12, let's see, what is the date? 1921. So, try to recap. A lot of stuff that you learn, you will see that we progress uh, from, and a lot of stuff are going to be re-enhanced every time when we get to certain type of like, for example, common source amplifiers, things like that. Yeah. Yeah, that's the February 19th, Monday. It's going to be the Monday, Tuesday. Yeah. Yeah, right. So next week I'll be traveling, so I can do because the time zone is a little bit tricky. Um, if you guys want to, uh, if you're going to meet me on Zoom over Zoom, that you can schedule or you can email me, so we can pretty much do it in the morning, like from say 7 o'clock here, San Diego time until I would say noon, the morning time I can do it. I'm in Europe traveling. I'm traveling. Yeah, I'm traveling on business. This uh and uh and then on Monday, the following Monday, February, is it February 17th or 19th? Today is 7/5. So 5 is the 19th. So February 19th, we're gonna have the next quiz. And for that day, I'm gonna open up my like office hour from noon. So if you guys want to come early, you can, I mean, you can always come early. I always have like today's student come at 1, so it's okay. But for that day, I'll make sure that I'll be in my office. So you have questions on chapter 8, anything regarding homework and quizzes and so on. This is just a little bit the caveat. What happened is our grader has not been cleared to work until today. So that's why some of the stuff has been behind, like posting homework solutions, grading the quizzes and so on. I apologize for that, but the university has a very rigid system and they have to go through the process to make sure she's qualified to work. I don't know what happened, why it's so slow. So that's a little caveat. Um, but the um, also with the homework, you'll see that some homework gets more and more difficult towards the next, towards the end of the later part of the homework, which is kind of on purpose. Our quiz doesn't usually go to that deep. So like today, a few students asked me if I could like redo the problem today, but I don't think we have the time. We want to cover the contents. But at some point, maybe I'll come back to cover those contents. But it doesn't mean you shouldn't do the homework. You still should do it because towards our final exam, you will see more difficult stuff that's going to be covered. Because what I found is that sometimes it's hard in the beginning to digest, like to connect all dots. You got here and there. So towards the end of the semester, and you'll connect everything together. So that will also make it easier. So, oh, that's what I thought. At that time, I didn't understand what is why, but now I understand more. So you connect them all together, so make it easier. But if you don't do the homework, if you don't, it will make you more and more difficult to learn. As I told you, chapter 5 is a review, 6 is a review, 7 is a review, 8 is where we start the real contents, but 8 is relatively simple, 9 gets more difficult, and 10 gets miserable. So that's how it goes. I mean, what can you do? So just saying that you have to do the homework, to catch up and understand the contents later. So anyway, so today we're going to cover part 2 of chapter 8. But you'll see today, some of the stuff is a repeat from chapter 7. So which is good, right? So just give you again, try to write this down in your memory, in your brain, say, okay, now I get it. So that's the goal. But before I dive into the basic gain circuit, I want to illustrate how a gain or amplifier, let's say. Sometimes we call it gain circuit, sometimes we call it amplifier. How does an amplifier work? You might remember in 210 or 330, you learn op-amp, right? So op-amp is an amplifier. But that op-amp is exactly a multi-stage amplifier we're going to build in chapter 9. So, but at the time you learn op-amps, you didn't know what's inside. It's just a functional block. So that's something like op-amp. But in general, you can represent any gain or any amplifier in a generic block. Has an input coming in and there's output going out. If you want to use this circuit, you would simply connect an input resistance. Sometimes it gets input source, and sometimes it would have internal resistance of the source. So in this book, they continuously use this V SIG or V signal and R SIG. And at the output, you can connect anything like a functional block, but you certainly can connect a load resistance, right? So here you get output. But often what's get confusing is that this gain block is not ideal. Like in op-amp, you probably learned it. It's an idea. It's got an infinity like amplification or many times, thousands. But in fact, most of the time, this is not ideal. So in a not ideal situation, this block becomes this equivalent circuit. So, and often there we don't have to connect it. So in that case, we'll just remove that connection so that we make it more like a generic. Oh, this is bad. So this is your, and then in part here, we call it R in, and in part here, we call it R out. And the R in is called the input resistance of the amplifier. That R out is called output resistance of amplifier. The gain over here is a current source, but we can also convert this into a voltage source by using source transformation, which means this equivalent circuit can also be written as over here. I just make a little bit difference here just so that I make this slightly different. The difference that I made is the voltage source. I made it on the top. Generally, the voltage source will be going down. But if it's going down, the gain is always negative. But if I make it here, the positive up and the gain becomes positive. So this is used to be like A times VI. So this is VI. And this is again R in VO and so on. So this voltage here is AV times AVI. So this is very useful gain block. Two input terminals, two output terminals. And why is this important? Well, because if I give you as any example, like I'm going to use this as example with the input voltage. I'm going to have this input voltage, have an internal resistance, and with this one, and I have this voltage source, output. Let me write down this so that we can start to solve the circuit. So in this case, you see the AV is a number, times 5, 100, 1,000, whatever that is number is. So when this signal comes in, this is V in. So what you're amplifying here is not V signal, not the sensor output. It's actually you're amplifying this. So I give this example, start with is that, okay. And also your load voltage, VO is over here, is not over here. So let's write down that VO, see what do we get. So in order to get a VO, first of all, we need to get V in. Can we write together? How much is V in terms of expression of V signal? It's a voltage divider, right? It's a divider, it's a voltage dividing between this and this. This one and this one, dividing the whole voltage over here. So we write it V in as R in, here, R in, over R in over plus R sig times V sig. And how much is VO? VO is the voltage divider between RL and R out. So we have RL over RL plus R out times A times V in. So overall, you now can write VO as a function of, because we plug this V in, like this V in to here. Then we got the overall, let me use this AV, means voltage output, becomes AV times R in over R in plus R sig times RL then times V sig. So we got the gain of the overall from now the gain is the actual circuit gain is the output over here over the input over here. But the middle, the amplifier, this is amplified. The amplifier really only amplify way in all the way to here. But the rest is what we need to get to the gain. So if you look at this gain, let me ask you a few questions here. What happens if R sig is, if I sig is like very big? Let's see, I sig equal to 100K and R in equal to 1K. If this two has a 100 times difference, what happens with the gain? You look at here. Very small. This is 1 over 100.01. And similarly, if I have R out, if I have R out is very big, let's say to 100K, I have RL is 10K. What happens now to my output? If my R out is 100K, my RL is 10K, which means my gain also only 1/10 of it's supposed to be. So ideally, if I want the gain to be like very big or maximize, what R in should you have? In this example, how much R in should you have? Over 100K? Yes, and then? Infinity, exactly. If R in is infinity, this becomes negligible, and this to cancel, I got the gain really unchanged. How about out? How much R out do we want? If I have the gain like really to reach maximum? 0. If this 0, RL, this is 1, which means this term becomes 1, this term becomes 1, so my overall gain becomes A times V sig, right? So that's what we're saying is for generic amplifier, R in should be big, but R out should be small. That's the generic amplifier. So now you think back, for what kind of amplifier do we have the input resistance as an infinity? BJT and MOSFETs, which one has? The MOSFET has an open circuit at the gate. So you got the infinity input resistance. For the BJT, how much is the input resistance? For the common source? Do you remember? It's R pi. So R pi is the internal. See, for MOSFET, you have an open circuit. And for BJT, you have this. So this R pi is R in equal to infinity. For BJT, R in equal to R pi. That's our generic amplifier. So much about this. Now we want to get to the equivalent circuits of the current mirror that we covered last time. Right? So we covered last time current mirrors, and then now we want to look at what exactly we can get for the equivalent circuit. So for this current mirror, what we're looking at is, because we're going to use this current source for many purposes in this class. We use it as like a load. We use it to bias the devices. But once you translate the DC biasing circuit into a small signal circuit, what do you know, normally we'll say, okay, current source is open circuit. That's in an ideal situation. But if you build a current source using these BJTs and MOSFETs as current mirrors, current sources, they're actually not open circuit. There is some sort of resistance. So in order to get that equivalent resistance for AC circuit, we are going to derive a small signal circuit. So the small signal, the way to derive a small signal circuit is we are going to add an input at the reference. So the reference IDY is our current source, like the current of the current mirror. But we're going to add a I, which is a kind of input, and see what happens. So for this, it's very easy. We can draw the equivalent circuit of these two MOSFETs, and then we can get the small signal equivalent circuit. So let's draw the gate over here. So we're going to draw Q1. We're going to draw Q2 over here. So Q1 has the gate connected to the this source is all connected together. And then for this one, we have this open. So we have this. Now we're going to put our RO2 with the circuit. So the gate is over here, and the gate is connected to RO1. The gate is both are connected together. So, and here we have I coming in. Yeah. No, actually, this gate, well, the other gate is not connected to source. Sorry. So, yeah, this Q2. Sorry, Q2 gate of Q2 is not connected to anywhere, but it's connected to the other source. So actually, so it should look like this. So this is D1. This is G2. And from here to here is VGS. And here is CM1, VGS. And here is GM2 and VGS. So right now we're gonna look at what happens with we're gonna get this output over here. Right. Yes, we are. Now the purpose of course this circuit is not to get a VO, but we try to get what are the output resistance going to be. So if we look at, we want to get the resistance over here of this one. And we're going to apply a VO over here. And we're going to get IO over here. And then let's cut out. And we would get this V out or I out. And then on the other hand, we are going to have So if we look at one of the things interesting, I think this circuit is interesting here is from G2 to ground, that's VGS. And this current source is GM2 times VGS. So therefore, we can convert this one into a kind of a current source, a kind of a resistance. So like this one here. So GM1, for example, GM1 times VGS1 is a current. And then the voltage is VGS1. So this becomes 1 over GM, which is equivalent to a resistance. So that's some resistance, some sort of resistance we can connect. So now this part, we redraw that circuit because the current, we're going to move it up this way, so make it better to understand. And here we can, let me see, why is it GM2 times VGS2? GM2 times VGS. Right, okay, got it. So here, so now we're going to look at here as R in, here we use R out. So the way to get R in and out is, well, like over here, I had example, I apply VO, I want to get an IO. So if you remember in the Thevenin circuit analysis, when you do this type of analysis, what you do is you would open the current source and short the voltage source. So in the sense that we're going to apply, like when we want to find out the way out, what we do is we would redraw the circuit like this. We would draw but since we are applying this VO, this is IO here. Now, this current source, we need to open it. We need to open the current source because when we apply voltage here, come in, we want to test how much the resistance is. We apply voltage here, we open this one. We open this one, this circuit becomes just two resistance by itself. And then how much voltage would you have here? 0. If the voltage here is 0, how much current do you have here? 0. Because this is GM times VGS. So VGS 0, so this current is 0. If this current is 0, what does it mean? Current 0 means open circuit. So with this open circuit, you apply voltage here, how much current do you get? Really just voltage divided by the resistance, right? So then in the way that how much resistance do you have? You look at this way. So just RO2. The resistance just I R out is equal to VO or IO equal to RO2. So in the sense that what we are talking about here is that what we are saying is the whole circuit over here, to the outside, it just looks like resistance. So in a way that we can draw the equivalent circuit to be something like this. Yeah. So that's how we did it. And then we did like this, we did all that. So really, the equivalent circuit of this current mirror, let me redraw the current mirror. So the current mirror here, so the whole thing here is going to be equivalent to a current source it's going to look like this, because then the current source has output resistance of RO2, and the current source is a reference current. This is extremely important because in the future, we're going to always come back to, okay, this current source, we're going to replace the current source with its output resistance and a current source. And that current source is for DC. So for AC small signal, the current source is open. So what we are saying is, well, the whole current mirror or current source, it just becomes the output resistance of the current mirror. So so here, we're gonna take a look at the basic gain cell again with a MOSFET. As we all know, this already, what is the name of this amplifier? We have CS, CG, CB, CD. This is the common source because the source is grounded, okay? And the input is at the gate. So this is a common source amplifier, but it got a current source at the drain. Instead, remember before we did this circuit, I'm going to redraw this over here. We always had an amplifier like this. Yeah, remember this is most of the time we had this one. Where the MOSFET we input the gate and we have a common source and then have a resistance at the drain. And when you calculate remember when you calculate the DC biasing and calculate whether it's in saturation or triode, we always had a like a resistance, not RL, should be RD. But instead of using RD, that we have to calculate the biasing and so on, we're going to replace that with I, with the current source. So now it's this circuit. So with the current source, with this previous circuit, we always draw the equivalent circuit pi circuit like this. And when we consider also the RO and RD, okay, and this is your V. That's how we draw the equivalent circuit of this one. But for that one, we have a little bit trouble because if you think a small signal circuit, that current source will be open. But remember from the previous slide, we got what? We got the current source is really equivalent to a current source in parallel with system RO. And here we call it RO2. So in this case, the equivalent circuit becomes RO1 is its own RO2. And this all ground. Now you can figure out what's the difference between, you might say, what's the difference between this and this? What's the difference between these two? Tell me, what's the difference? Well, circuit looks similar, right? But there's a huge difference. The difference is this is RD, but the other one is RO2. Well, you say, well, it's a resistance. What's the huge difference? Well, the huge difference is that RD used to be very small, like 1K, for example. But RO can be huge, 50K. So we can, let's say we want to calculate the gain of the circuit. We can do maybe, let me see if I have an example here. Yeah, I don't have an actual numeric example, but no, actually I do have one. So let's say you get a RO, you get I GM equal to 5. And we have RO1 equal to 50. RO2 equal to 50 kilo ohm. And RD equal to 1 kilo. See, let's see how much gain we're going to get for this one and how much gain we get for this one. So for this one, the gain is going to be GM times RO in parallel with RD, where GM is 5 times RO is 50 in parallel with RD is 1K. And you probably know 50 and 1 in parallel, how much resistance would you get? Almost 1, yeah. So this just really equal to 1 volt. Okay, and then we look at the other one. The other one we have gain equal to GM times RO1 in parallel with RO2. And they are each 50. And how much is the gain of these two in parallel? 50 in parallel is 25. So 25 times 5. So it gives you 125 gain. But the other one gives you only 5. And you can see the difference is 25 times. So that's why it's important to use a current source to bias the MOSFET instead of a resistance. And further, in our IC design, it's very difficult to create a resistance on a silicon, but it's very easy to create a MOSFET on a silicon. You can create 1 million like MOSFETs on a very small chip, but it's impossible to create 1 million resistance there. You may create a few, but you still need a resistance. But resistance takes a lot more area, to create it. Because silicon is silicon. Silicon is easy to make semiconductor. It's not something you use to make a resistance. So that's why it's important. So here, sorry that it's covered there, but it's okay. You got the basic idea. So we probably can go further with BJT. So the difference with BJT, I'm going to go quickly through this, is the equivalent circuit becomes, I'm not going to draw the equivalent circuit for the resistor anymore, but simply draw the equivalent circuit for the BJT. So if you still wonder, how do I get the gain? Well, the gain is basically V out over V in. And in this case, because this is GM times V pi is equal to GM times V in. So we got this is V out is going to be GM times V in. We'll have to forget minus sign here. And then multiplied by RO1 in parallel with RO2 and divided by V in. So this will become minus GM times RO1 in parallel with RO2. If you don't have a current source, if you have a resistor at the collector, you would have the gain RO2 replaced by RC. And RC could be again in the kilo ohms, but RO2 could be in the tens of kilo ohms. So you basically increase the gain by many times, 20 times, 10 to 20 times, okay? Yeah, so this is basically, we already covered it. So basically we are replacing this current source. Here in the previous example, we did this. But how do you get the current source? Is really just like this. Well, you might say, well, that's not, right? Because that one is not a current source. In fact, in the book, and also people like to do this, they simply neglected the mirror part. They only left the actual current source. So in theory, this would be something, oops, I don't want to amplify. So this will be something like this. So in theory, they're just missing that part. So you see what happens now, Q2, let's call it Q3, Q2 and Q3 now makes up pair of current mirror. But in the drawing, because that part has nothing to do with this amplification, it only provides the current reference, so we draw the circuit list. And when we draw the circuit list, we already derive the equivalent circuit, which is current source in parallel with its resistance. And therefore, the overall equivalent circuit is what we draw from the previous slide. So we're not going to repeat it here. You got that. And in this section, they talk about the practical amplifier. The reason that if we go here, you will notice that there's a problem. There's a problem because if this is like a ground and this is ground, for the upper MOSFET, you really have to have a PMOS instead of an NMOS. This is the current source on the top. But if the current source at the bottom, you really have NMOS. But it's on the top, we use PMOS. So for that PMOS, this becomes, in this circuit, you figure out the amplifier is right over here. And here, this part is the current source. But here is this current amplifier. So the whole thing up there can be replaced by, basically, if you want to compare, just compare this. This amplifier, and this resistance in a traditional circuit, but we replace this one with a current source, with Q2. So that's exactly, back and forth, just to emphasize your, train your brain to remember what this is. So now you might ask, okay, it's good to have the gain that is increased by replacing the resistance with a current source. We can increase gain. The next question is, how do we further increase gain? Well, 100 from 5 to 125 increased by 25 times, which is good, but not good enough. What if I want 5,000? And so from 125 to 5,000, it's another, like, how many times increase? 50 times increase, yeah? Almost 50 times increase. How do you increase that by another 50 times of the gain? Well, one of the things we can do typically, we can put them in series, like 100, another 100, so that gives you 10,000, right? So that's easiest one to do. That's sometimes we call it multi-stage. But in a IC design, they want, oh, well, that's okay, but I want to see a single amplifier. I want to reach very high gain. How do I do that? So this is where we can increase the gain. So in this circuit over here, we have two circuits, the top circuit and the bottom circuit. So the top circuit gives you the gain. If you look at the gain without the load, now everything we talk about here is without anything connected. Simply saying, okay, this amplification, this is open circuit gain. With the open circuit gain of the top circuit, what do you get? Well, we know that, if you still doubt how we get it, you can always write VO equal to this GM times VI times RO1 negative, and the gain AV becomes VO over VI, gives you minus GM times RO1. In the bottom circuit, they said, well, instead doing that current source or load whatever, we're going to add something here. And this something can be like Q2 we had before. If we will do that, you increase your gain by 25 times. Okay, but what if we put something here that can give you even much bigger resistance? So this work here, we give that times K. So if we have K times RO, now you have your gain equal to minus GM times K times RO1. So here, basically, we need to figure out how to increase that thing by a K, by K times. So this is what really the some of the stuff that I think we're going to get to that by later on is how we increase the gain by putting that block. It's not in today's lecture, but it's probably in the next lecture that is recorded. But before that, let's move on to some more like difficult stuff is the common gate amplifier. Now this is again sort of a review, but a little bit more complex equivalent circuit. If you have a common gate amplifier means the gate is going to be grounded. If gate is grounded, the input is coming here at the source. And always, you can always, this current source and this RS. So you can always supply a voltage source, that's okay too. But for simplicity, current source and voltage source can be always transformed to each other. So that's okay. So in this case, we use input current to solve for the circuit. If you draw the equivalent circuit, well, this actually is not the equivalent circuit. So what they're doing is, let me start by drawing let's say the pi model, and to figure out how the circuit would work. And we can always draw the T model as well. So we draw the MOSFET, we start with the MOSFET. Again, this is important. I mention this all the time. When you draw a small signal equivalent circuit, always start with the MOSFET. And then mark down the names of each of the terminals so that you know what to connect. This is source. So at this point, we're going to figure out gate is grounded because it's common gate, so gate is going to ground. And the source is connect these two things here. And the drain is connect to RL. So this drain connects to RL to ground. And the gate is grounded. And source is connected to this circuit looks a little bit, with a little bit more like a difficult because it does involve a couple of elements. There's current here, the resistance, the current there, the resistance. So if you look carefully, there are two nodes. One node is here, there's a super node. There's a node at the gate, at the drain. So if we want to solve this, we would have to kind of write this two nodal equations. But since we can do source transformation, if we do that, this will make this circuit a little bit easier because we can transfer this two into a voltage source in series with a resistance. And the other one too, we can do that as well. So if we do that, we will have something, I have enough space to draw it here. So I'm going to leave the gate because this is also an important part. So this one becomes a voltage source and a resistance here, ground. And here we have resistance, and then we have a voltage source. Okay, should we look at how I draw the voltage source? This is positive up, this is positive down. because the voltage has always to the positive terminal of the voltage source is always the current coming out. I mean, think it, you have a battery, where would the current come out of a battery? From the positive terminal, right? So I know some students still get confused. When I transfer current source into voltage source, how do I know where to put the positive sign? Well, because the current has to come out of the positive terminal, so that's how you do this. So if we do this, we got this is RO1, this RL, and this RS, and this is I signal times RS, and this is GM times VGS and times RO1. And this is VGS. Because there's no current here. Remember, there's no current. So we should be able to get like current this way. So we can define a current over here. So we define a current over here. That's called IL. So we get IL equal to basically this 2 voltage source, GM times VGS times RO1 minus SIG times RS. There's 2 voltage source. They're opposite to each other. Divide by RM. RM. RS plus RO1. So you got that. Now, the importance here is to look at what is VGS. What is VGS? So really, VGS is the voltage from here to here. Or VGS from here to here, right? So VGS is from here to here. There's a voltage out here. So the voltage drop here. So VGS equal to IL times RS plus ISIG times RS. So you got VGS. Here we can plug in VGS to here. And we can derive the relation between, we can find our IL and as a function for ISG. So from there, we can get the gain. See if I have another circuit. So you get the gain is going to be, and this is called a current gain. So which is going to be AI equal to IL over ISG. So it's a little bit of, if we want to, probably don't have time to do it in this class to derive the actual equation, but this is given in the book. The final result is going to be so I got the gain circuit over here is 1 plus, let's see what is the gain here. Resistance, IO equal to, yeah, so the set of derivations is given in the book, but we can derive them one by one. And I don't have time today here. But I can give you all the equations. I mean, in the book, we don't have to really. But what happens in this book? They find some like a little bit an easier way to determine like what is the input resistance and output resistance, and then they put this together to solve the circuit instead of solving for like a separate nodal analysis or loop analysis. They save a little bit of time. So that's why they got this circuit over here. So they use this to represent this. But here, they don't know what this IS is. So that's the key. This is not GM. Remember, this is not GM times VGS. So this is a virtual equivalent circuit of that thing. So now, in order to do this, we have to find Rin, we have to find this. So in order to find R in, they use this circuit over here. So we provide, so here, remember previously what was here is Ix and Rs. So they simply remove that Rs. So this one here is but they take out the Rs as an external to the MOSFET. So they look at the R in. And by doing this circuit, you can, again, it's very easy to do the mathematics because doing the voltage transformation, you get this through, and then you can do loop analysis. And then you can find Ix, and you can Ix, and then use Ix over Vx, we can get the input resistance. So input resistance is and you can write Vx equal to here we have to transfer this one a little bit to Gm times VGS times RO. This positive here minus and then plus this Ix times RL. So we're plugging this in here. We should be able to get the, and then of course we have to write VGS. And VGS in this case, what is VGS? The VGS is from G to S, but G is ground. But here from S to ground is Vx. So VGS is minus VGS. So plug this in, you get R in equal to just RL plus Gm times RO. So you get the input resistance. And then similarly, we can get the output resistance. By doing output resistance, we do this Vx over Ix again, but now Vx is connected over here. So that's your output resistance. And now, but now they put Rs back. So they, again, doing the voltage transformation here, you get VGS. Now see VGS equal to minus Ix times Rs. Yeah. So, and then you can write Vs equal to minus Gm times VGS times RO, then plus Ix times Rs. So plug in VGS here, so you got the relation between it's called Vx. So now you got this, plugging this back to here, we got R out. And so I'm not gonna repeat that. Yeah, I think pretty much we covered most of what I wanted to cover here today. If in the sense that in the book, it always tells you about impedance transformation property of any amplifier. Because the MOSFET is typically it's amplified. So in addition to amplify a voltage or current, it also amplifies the resistance, input and output resistance. And the ratio is given by Gm. So in this case, you get input resistance and derived like this and output resistance over there. So if I have time after next week, I'm going to go through a few of these derivations for you. So this common base, impedance, okay. So I think I'm going to stop here because we need to leave time for the quiz. Let me so I will post the slides and also the lecture. The slides will be posted, and I'm probably going to add a few stuff over here. Okay.